The three-body problem, one of the greatest physical mathematical problems that has haunted humanity for centuries. Join us in this video as we explain what this problem is from a physical mathematical perspective and its connection to space exploration. In 1687, Isaac Newton published his Philosophiae Naturalis Principia Mathematica, one of the foundational works of physical sciences. This work literally changed history, primarily due to a simple, seemingly harmless equation, the law of universal gravitation. In a physical system with two celestial bodies, they are mutually attracted by a force called gravity, which increases with the product of their masses and decreases with the square of their distance. The law of universal gravitation is thus a solution to the two-body problem, where two bodies are bound by gravitational force. Essentially, how these bodies move within the system is dictated by the law of universal gravitation, from which the so-called three laws of Kepler are derived. These laws tell us that orbiting bodies move in an elliptical motion, following a geometric shape called an ellipse, where the orbited body occupies one of the two foci. In reality, it's not that simple. Both the orbiting body and the orbited body are both orbiting around the center of mass of the system, a balance point between these two objects. When we say a planet orbits around the Sun, it is not entirely correct, because both the planet and the Sun orbit around this center of gravity, which is very close to the Sun. The two-body problem is well defined because, theoretically, if there are only two bodies and we know their orbital parameters, we can calculate their position at any given time. However, in reality, there are other bodies that influence the system, making it difficult to know the exact orbital parameters. But what happens if we add another body to the system? If we go from the two-body problem to the three-body problem? Answering this question is important from a practical perspective, considering the Earth, the Moon, and the Sun, or the Sun, the Earth, and a satellite, or the Earth, the Moon, and a probe directed towards the Moon. The issue is that the three-body problem lacks a clear and simple solution like Newton's. Newton himself realized that adding a third body made the situation much more complicated. In Proposition 66 of the first book of the Principia, he examined the case of two lower mass bodies orbiting a more massive one, but kept the description qualitative because he did not know how to handle the problem. He defined this proposition as imperfect. This problem became evident with the motion of comets, whose trajectory around the Sun could be altered by passing close to a planet. This could perturb the comet's orbit, leading it onto different paths. If we replace the comet with a space probe, the problem becomes crucial for robotic planetary exploration. The three-body problem has been known since at least the 17th century and continues to engage astronomers, physicists, and mathematicians in seeking a useful practical solution. It can be generalized to the n-body problem, where n is a number greater than 3, considering a solar system with one star, 8 planets, thousands of dwarf planets, millions of asteroids, tens of billions of comets, and over 250 satellites. However, we will limit ourselves to the three-body problem. In 1892, French mathematician Henri Poincaré published New Methods of Celestial Mechanics, addressing the three-body problem without finding a real solution, demonstrating that a solution does not exist. He showed that, mathematically, the dynamics of three bodies bound by gravity are unpredictable. However, we solve the problem from a practical standpoint. How do we launch space probes and make them pass close to planets without considering the three-body problem? In 1915, Finnish mathematician Carl Sundman published a theoretical solution to the problem, followed in 1991 by American mathematician J. M. Wang's solution for the n-body problem. These solutions, however, are not practically useful because they consist of an infinite series of terms, making them too slow to calculate even with modern computers. Numerical solutions, obtained through computers since the 1960s, allow us to approximate the solution through successive calculations, getting closer and closer to the actual motion of the bodies without ever fully reaching it. This method allows us to solve practical problems like calculating the trajectories of space probes, while always maintaining a certain degree of uncertainty. Lagrange points, for example, emerge as a solution to the restricted three-body problem, where a third gravitationally insignificant body can find equilibrium between two main bodies. Gravitational slingshots, on the other hand, are a practical example of exploiting the three-body problem to increase the efficiency of space missions. This concept was first used by Michael Minovich in the 1960s, changing the history of space exploration. The three-body problem is also relevant for human exploration of the Moon, where the Orion capsule follows trajectories calculated by exploiting the restricted three-body problem. The same applies to Trojan asteroids, geostationary satellites, and exoplanetary systems with 2 stars. Thank you for watching, and we invite you to subscribe to the channel, activate the notification bell, and like the video.